Hi, this is the video for Chapter 6 about discrete probability distributions. The two sections that we'll cover from Chapter 6 are Sections 6.1 and 6.2. So starting with Section 6.1 about discrete random variables, the objectives for this section are 1. Identify discrete random variables and discrete probability distributions. 2. Construct probability histograms. And 3. Compute and interpret the mean of a discrete random variable. Objective 1 is to identify discrete random variables and discrete probability distributions. So before we define a discrete random variable, we have to talk about what a random variable is. A random variable is a numerical measure of the outcome from a probability experiment, so its value is determined by chance. And notice here that we are specifying that this is a numerical measure. So in the case where our outcomes have been given as categories using words, we have to find some way to change that to a numerical value. Random variables are denoted using letters such as X, and the variable has a single value for each outcome of a probability experiment. And again, when we're talking about random variables, these values have to be numerical. When we're specifically talking about discrete random variables, we talked in Chapter 1 about the difference between discrete and continuous variables. This is the same thing. A discrete random variable has either a finite or a countable number of values. And countable refers to the fact that there might be an infinite number of values, but they result from a counting process. This also means that the values can be plotted as points on a number line with spaces between the points. Here's some examples of discrete random variables. We'll take some of the probability experiments that we've already talked about and their sample spaces and see how that relates to the values of the discrete random variable. So one experiment is rolling a die. The sample space would be the numbers 1 through 6. So we could make our values of X, our random variable, be those same 6 values. So our possible values of X would be the numbers 1 through 6. Another experiment we talked about earlier was selecting a part and inspecting it, and our sample space was that the part was either defective or non-defective. Now, to think of this as a discrete random variable, we would have to put numerical values on defective and non-defective. A lot of times we'll choose 1 for one of the values and 0 for the other value if we only have 2 values. So in this case, we could decide that 1 would stand for a defective part and 0 would stand for a non-defective part. Another experiment we've talked about is drawing a playing card from a deck and recording the suit. So the possible outcomes here were hearts, diamonds, clubs, and spades. And again, we would want to assign numerical values to these 4 different outcomes. How we would do that would depend on what we were going to do with the information. So for example, if we were actually playing a game where we were drawing a playing card and the suit made some kind of difference about how much money we won or lost, then we could use that to put a numerical value on these 4 outcomes. So for example, we might use these 4 numerical values for those 4 outcomes. And again, what these values are would depend on the situation. Here's another example. If we had an experiment where we draw 5 M&Ms from a bag with replacement and record the number of red M&Ms drawn out of the 5, our sample space, or our possible outcomes, would be any value from 0 up to 5. Because if we're looking at the total number of red M&Ms drawn out of the 5 draws, we could have gotten no red M&Ms or any number in between, or we could have gotten all 5 red M&Ms. So again, the values of our discrete variable here would be anything from 0 up to 5. Now let's look at some examples of discrete probability distributions. And these are the same type of probability distributions we talked about in Chapter 5, only now we're using our discrete random variable x, so our values for our outcomes have to be numerical. With discrete random variables, as long as there are a finite number of values, then you can just make a table to represent your discrete probability distribution. So again, for our experiment of rolling a die, here are our values of x, and these would be the classical probabilities for each value of x. For the experiment of selecting a part and inspecting it, and here supposing that 8% of the parts produced are defective, then remember on the last slide we decided to use 1 to stand for a defective part and 0 to stand for a non-defective part. So the probabilities would look like this. This would be our discrete probability distribution. And finally, if we're drawing a playing card and recording the suit with the values that we defined for the variable on the last slide, our probability distribution would look like this. Again, the only difference between what we're doing here and what we did in the last chapter is that we're giving numerical values, since we're actually talking about the values of a variable. And remember, again from the last chapter, that there are two conditions that have to be met to get a valid probability distribution. Number one is that all of the probabilities have to be between 0 and 1, and the second one is that the sum of the probabilities must be 1. So the values of our probabilities cannot be negative and they cannot be greater than 1, and they also have to add up to 1 if we add up all the probabilities in our table. So that's true here, that's true here, and that's true here. So all three of these would be valid probability distributions. The other thing to note here is that it doesn't matter what the values of x are. Those can be anything. They can be negative or positive. For example, we had some negative values over here. To be a valid probability distribution, what matters is the values of the probabilities in this column. Objective 2 in this section is to construct probability histograms. So we talked about histograms in Chapter 2, and a probability histogram is very similar to a relative frequency histogram, except that the vertical scale shows probabilities instead of relative frequencies. For a discrete probability distribution, we typically use 1 bar for each value of x, so for each outcome. Here's an example of a probability histogram, and this would be the case where these are all possible values of x, everything from 0 up to 12, and each one is represented by 1 bar. So for example, the probability of the outcome 8, according to this histogram, would be about 0.12. The outcome with the largest probability here would be the 10, which has a probability of about 0.28. Notice that there are several over here on the left side which must have very small probabilities, very close to 0, since we can't even see them on this histogram. Some more examples of probability histograms taken from the probability distributions we already looked at. In this one, we only have 2 possible outcomes. So we're only going to have 2 bars on our graph. So we have the 0, which has a probability of 0.92, and the 1, which has a probability of 0.08. Another example from our experiment of rolling a die. In this case, every outcome has the same probability. So our probability histogram is going to look like this. It's uniform across the top because every one of these values has a probability of 1/6. Objective 3 is to compute and interpret the mean of a discrete random variable. So in this section, we have formulas actually for the mean and the standard deviation of a discrete random variable. Here's the formula for the mean, The most important thing to notice here is the notation. So we use this symbol to stand for the mean of a discrete random variable. Another thing we call this is the mean of a probability distribution. So we use the symbol mu with the subscript x to represent the mean of our probability distribution. Now again, this formula tells you what to do, but we will, for the most part, use technology to calculate these. So the important things in this formula are that x is the value of the random variable, p of x means the probability of that value, and the mu of x is the mean of our probability distribution. Now to actually compute the mean, we're going to use basically the same process as we did for approximating the mean of a frequency distribution. The difference here is that instead of class midpoints, we're going to use the values of the variable x, and instead of frequencies, we're going to use the probabilities in decimal or fraction form, not in percentage form. Here's an example. This probability distribution represents the number of DVDs a person rents from a video store during a single visit. We're going to compute the mean of this probability distribution. So we're going to use a similar procedure for what we did for approximating the mean from a frequency distribution. If we're doing this by hand, we will multiply each x value by its probability, and then we'll add up the results. If we're using our TI-83 or 84, we will enter the x values into list 1, we'll enter the probabilities into list 2, and then we'll use the one variable stat function. Either way, we should get the same answer, and that is 1.49 for the mean. Now, how do we interpret the mean of a probability distribution? The mean of a random variable represents the mean of the outcomes of the experiment in the long run. In other words, if the experiment is repeated, as the number of trials increases, the mean of the outcomes gets closer to the mean of the random variable. The mean of the random variable is also called the expected value, because this is what we would expect to happen in the long run. And this value is sometimes denoted by E of x. So E of x is the same as the mu sub x. Here's an example. This is the same probability distribution for which we already calculated the mean. We found that the mean was 1.49. Now we're going to interpret this as the expected value of the random variable. So our expected value is the same as the mean, so it's 1.49. So to interpret this, let's consider each customer's visit as one trial of this experiment. In the long run, the average number of DVDs rented by customers during a single visit is 1.49. That's what we mean by the expected value. For example, in 1,000 customer visits, the total number of DVDs rentals we would expect is 1,000 times 1.49, or 1,490. Here's another example of expected values. Suppose we're playing a game where one card is drawn from a 52-card deck. If a face card, a jack, queen, or king, is drawn, the dealer pays the player $5. For an ace, the dealer pays $8, and for any other card, the player pays the dealer $3. Find the expected value of this game for the dealer. So first we need to create the probability distribution table. The outcomes, or the x values, will be amounts of money. Since we're finding the expected value for the dealer, amounts that the dealer pays out will be negative, since they're losses, and the amounts that the dealer receives will be positive, since they're gains. So here would be our probability distribution. The three different outcomes are that the dealer pays the player $5, which means the dealer is losing $5, so we make that a negative number. Another outcome is that the dealer pays out $8, so we'd have -8. And the third outcome is that the player pays the dealer $3. So here the dealer is gaining $3, so that's a positive 3. Now we can figure out the probabilities for these three. This first one, the -5, was if the card drawn was a jack, queen, or king. Since there are 12 cards that are either a jack, a queen, or a king, the probability of that would be 12 divided by 52. The -8 was if an ace was drawn. Since there are 4 aces, that probability would be 4 over 52. And then we have the rest of the cards, which out of 52 we have 36 cards left. Any of those cards, the dealer gets paid $3. So that probability would be 36 over 52. Now we're trying to find the expected value of this game, which would be the same as the mean of our probability distribution. And if we calculate that using either by hand or using our calculator, we get the value of 8 over 52 or 31 cents. What this means is that in the long run, so after many plays of this game, the dealer can expect to gain an average of 31 cents per play. Now obviously, no one play is going to get the dealer exactly 31 cents. Again, this is looking at many plays of the game, 100 plays or 1,000 plays, and this is the average gain that the dealer makes per play. For example, if the game were played 100 times, the dealer can expect to make a total of 100 times the expected value. So he can expect to make a total of $31.